So in this particular segment, we are going to talk about some theorems on area. Okay, theorems on areas of triangles. So let us consider that there are two triangles, or rather let us first reconsider the formula for area. So area of a triangle is given by half multiplied by the base multiplied by the height, right? And over here the base and height are perpendicular to each other. So if I have a triangle, so let's construct a triangle here. So we have a triangle, say PQR. Okay, consider the triangle PQR. If you consider QR as your base, so if I consider QR as my base, then dropping a perpendicular from P right onto the base, this perpendicular, this is called the height, right? So if the red part is considered as the base, then the height is perpendicular to the base. Similarly, if I consider PR as my base, so let's mark that as the base. So if PR is marked as the base, then from the opposite vertex I have to draw a line which is perpendicular to this base, right? And this is the combination of base and height. So if I consider this base to be B1, if this base is B1 and this height is H1, then this base will be considered as B2 and the height corresponding to it is considered as H2, right? So I know that area of this triangle PQR can be written as half into B1 H1. It can also be written as half into B2 times H2. And of course, if I consider the side PQ as the base, so if this is the base B3, then the height corresponding to it that is drawn from the vertex R, right? W height can be considered as the altitude of the triangle. So in a triangle, you will notice that there are three combinations of base and height that you could consider, and the area of the triangle is going to be half into base into whatever height corresponds to that particular base. Another thing that we should understand is if I have an obtuse angle triangle, so consider that I have an obtuse angle triangle, say triangle ABC. Let's write the vertices. So if I have triangle ABC, then because B is an obtuse angle, if I consider BC as my base, then the altitude corresponding to it is going to lie outside the triangle and it's going to be perpendicular to the base, right? So I can say that this particular line is the base, right? So this is the base and this is my altitude. This is the height, correct? So the area of this triangle, if I mark this point as D, the area of triangle ABC will be given as half into base is BC multiplied by the height is AD, right? So this gives me the area of the triangle ABC. Now let's consider different combinations for the triangles. So let's now take up the next diagram. So let's consider two triangles, okay, with the same or equal base. So let's construct a triangle over here. Yeah, so this is triangle ABC. This is triangle ABC. And let's consider another triangle here, which is triangle ABD, right? So let's consider these triangles. So I have triangle ABC and another triangle is DBC. So now if you notice, these two triangles have the same base or equal base and their heights are however different. So if I mark the heights, the height of the triangle ABC is shown by the red line, whereas the altitude of triangle ABC is shown by the blue line, right? So these are the two different altitudes of the two triangles. So if I consider area of triangle, let's mark these as P and Q. So if I consider area of triangle ABC, then I can write it as half into the base. The base is BC. The base is BC multiplied by the height. The height in this case happens to be AQ, right? Similarly, if I consider area of triangle DBC, then this is going to be half into the base. What is the base of the triangle DBC? It is BC multiplied by the height. The height is DP, right? So that's the altitude of the smaller triangle. So now if you take the ratios of these two areas, this is going to be half is going to cancel and BC and BC is also going to cancel. Therefore, what we get is area of triangle ABC divided by area of triangle DBC. Area of triangle DBC is given by AQ upon DP. Therefore, I can say if two triangles have the same base, then the ratio of their areas, is equal to the ratio of their altitudes. Right? So this is the first theorem that we have learned right now. That is based on the areas of triangles. If two triangles have the same base, then the ratio of their areas is equal to the ratio of their altitudes. So this particular theorem is going to be useful when we deal with problems that are based on areas as well as the ratio of the sides. So I will pause for a minute. I will let you take a look at this particular question, or rather this particular proof, and then we will continue with the next part. Okay, now let us consider the next case. The next case is going to be triangles with the same altitude but different bases. So look at the following figure over here. In this figure, we have three triangles. One is triangle ABC, the other is triangle ACD, and the third one is triangle ABD. So these are the three triangles that I can spot in this particular picture. Their bases are definitely different. So right now they have the same altitude. So how can I say that? I can say that because if you notice, I can draw a line which is parallel to BD. Okay, this line is parallel to BD, and the height, if I consider BC, CD or BD as the base, the height is basically the distance between these two parallel lines, right? So these are the two parallel lines. The height of the triangle is nothing but the distance between these two parallel lines. So now if I were to draw the height of the triangle ABD, say let's consider this red line to be the height of the triangle ABD, then this is also going to be the height for the other triangles as well, right? So if I consider area of triangle, say ABC. So let's consider area of triangle ABC. So right now I am picking the green triangle over here. So you will notice that this area will be given by half into the base is BC, multiplied by the altitude corresponding to it, which is H. Yeah. And now let me find the area of the triangle. So now let us shade this particular portion. So now I am going to find the area of triangle. Just a minute. Yeah. Let's find the area of triangle ACD. So area of triangle ACD will be given by half into, if I consider CD as my base, again C is an obtuse angle vertex. So if CD is the base, then again H is going to be the altitude, right? So I will write this as half into CD multiplied by the height, which is H. Okay. And if I were to take the complete triangle, so now let's try to take the complete triangle into consideration. That is area of triangle ABD. So area of triangle ABD will be written as half into the complete base is BD multiplied by H. So if I were to take the ratio of the areas now, I can say that area of triangle ABE divided by area of triangle ACD is given by half into BC into H divided by half into CD into H. Now half cancels and HH cancels. Therefore, the ratio of the area is, I should have taken ABC and not ABE. Okay, let me correct that over here. Yeah, it should have been ABC, right? So area of the triangle ABC divided by area of triangle ACD will be given by BC divided by CD. This is nothing but the ratio of their bases. So consider ABC. ABC is the triangle which is colored in the orange color now, and ACD is colored in the blue color. You will notice that because the altitude is same, the ratio of the areas, so the ratio of their area, so area of triangle ABC divided by area of triangle ACD, this is given by BC upon CD. So what I can say is, if two triangles have the same altitude, then the ratio of their areas is given by the ratio of their bases, right? So this is the second theorem that we have learned from this particular question. The earlier theorem was, if two triangles have the same base, then the ratio of their areas was the ratio of their altitudes. Here, if the two triangles have the same altitude, then the ratio of their area is same as the ratio of their bases. So again, I'm going to pause for a minute. By the way, let's also find some more ratio of areas here. So let's take area of triangle ACD divided by area of triangle ABD. Yeah. So if I take this ratio, it's going to be half into CD into H divided by half into BD into H. Half cancels, H cancels. Therefore, this ratio is CD upon BD, right? So ACD is the blue triangle and ABD is the whole triangle, if you notice, right? So the ratio of the area will be, the base of ACD is CD divided by the whole triangle's base is BD, right? So this gives us the area, the ratio of their areas. So again, I'm going to pause for a couple of minutes, and I will then continue with the next case. Okay, now let us consider the next case. So now let's consider the third case. The third case is when the two triangles have equal base as well as equal heights, right? So here let's consider triangle ABC. So I would say consider triangle ABC as well as triangle ABD. Yeah, let's consider these two triangles. Now these two triangles have the same base, which is AB, and they are also drawn between the two same parallel lines. If you notice, do you notice that the altitude, if I consider AB as the base, then the altitude is going to be the distance between these two parallel lines, right? And therefore the height is going to be the same. So what I will do is, let me draw the two heights. So one height is H1, right? Let me construct and mark it. So this height is H1, and let's mark the second height, which is H2. And we know that because ABD is obtuse angled at B, I can definitely draw the altitude outside the triangle, right? So if the height of triangle ABC is H1, then the height outside is also going to be H1, because it is the distance between the two same parallel lines. So what is the area of triangle ABC? Area of the triangle ABC is given by half into base, which is AB, multiplied by H1, and area of triangle ABD is given by half into AB into the height is again H1. You will notice that both the areas are equal, which means that area of triangle ABC is definitely equal to area of triangle ABD, and therefore the two triangles have equal area. And that's quite obvious. We know that the main formula for area of a triangle is half into base into height. So if two triangles have the same base and equal height, then definitely their areas are also bound to be the same. So whenever you have problems related to areas of triangles, always try to see if the two triangles have the same base and different height, or whether they have the same heights but different bases, or whether they have the same base and same height. So this is the third case. Again, I'm going to pause for a minute, and then we will take the next case, which is when two triangles don't have the same base or the same height. So now let's consider the case number 4, where two triangles have different base and different altitudes. So here I have triangle ABC and triangle TBE, where the bases and altitudes are different. So I have shown that DP is the altitude of triangle BED, and AQ is the altitude of triangle ABC. Therefore, what I can do is, you will notice that both the triangles have different base. So for example, if you take triangle BED, that is this triangle, BE is the base and DP is the altitude. Whereas if you take the larger triangle, the whole triangle, then in the whole triangle BC is the base and AQ is the altitude. So I can write the equation for the area of both the triangles. Both the triangles in this case have different base and different altitudes. So area of triangle ABC will be given by half into base is BC multiplied by the altitude, which is AQ. Similarly, area of triangle DBE will be given by half into base of DBE can be considered as BE multiplied by its altitude. What is the altitude? The altitude is DP, right? And therefore, if I find the ratio of their areas, area of triangle ABC divided by area of triangle DBE will be given as half into BC into AQ divided by half into BE into DP, right? So half cancels. Therefore, this becomes BC upon BE multiplied by AQ upon DP, right? So now BC upon BE is nothing but the ratio of their base, and AQ upon DP is nothing but the ratio of their altitudes, right? And therefore the ratio of their area is given by the ratio of the base multiplied by the ratio of the altitude. So we have considered all possible cases, all 4 cases. In one case we had equal bases, in the other case we had equal heights, in the third case we had both equal height and base, and in the last case we had different heights and bases. So let me now pause this for a minute or so, and then we will summarize all that we have learned so far. Okay, let us now summarize all that we have learned. So this is what we have learned so far. If two triangles have the same base, right? If two triangles have the same base, then the ratio of their areas equals the ratio of their altitude, right? Or if two triangles have the same altitude, then the ratio of their area equals the ratio of their base, If two triangles have the same base and altitude, the ratio of their area equals 1, or it means that the areas are equal, right? And the last thing that we concluded was, if two triangles have different bases and altitudes, then the ratio of their area equals product of the ratio of their bases and the ratio of their altitudes. So now these concepts are very useful, especially in case of trapezium. So we will take up a trapezium and we will try to understand how we can apply these ideas to problems in a trapezium. And whenever you see two triangles and if the ratio of their area or ratio of their bases or ratio of their altitudes is being asked, then these theorems are going to be extremely handy. So now let us take up a trapezium and see how we can apply these different ideas to the different triangles that the trapezium has. So let's take up this trapezium. This is a trapezium where AB is parallel to DC. Okay, and the point of intersection is O. So first I want to now consider triangle ABD and triangle ABC. Okay, so let me just shade these triangles for your reference. So this is the triangle ABD that we are talking about, and then we are also talking about the triangle ABC. Okay, so let's shade ABC again. ABC is over here. So these are the two triangles that I'm talking about. So what I can say is these two triangles, so let me shade the other triangle also. So these two triangles are triangles ABD and ABC. They have the same base. AB, right? And they have equal altitude also. Equal altitude means they are between the two same parallel lines, that is AB and CD, right? So these two triangles have the same altitude, and therefore I can say that area of triangle ABD will be equal to area of triangle ABC. The reason being, these two triangles have the same base as well as the same altitude, right? So if I were to just show you the altitude is the perpendicular distance between these two parallel lines, and for both the triangles this altitude is going to remain the same because these triangles are these lines are actually parallel, right? So this is the altitude for ABC. ABC's altitude will lie outside because B is obtuse angled, and for BAD the altitude will lie outside, that corresponds to base AB, but because the lines are parallel these two altitudes will be equal, right? So I can say that area of ABD is equal to area of ABC. Similarly, now I want to consider the next pair, which is consider triangles ADC and triangles DBC. Okay, so now let me shade those two triangles. So one triangle is ADC. ADC is this triangle, and the other triangle that I want to consider is triangle DBC, that's this triangle, right? So we are considering triangle ADC and triangle BDC. You will notice that these two triangles have the same base. They have the same base, which is DC, and they also have equal altitude, because again the altitude is the parallel line between these two lines, right? This is the equal altitude, and no matter where you measure this altitude, the altitude always remains equal, right? So whether you measure the altitude here for triangle BDC or whether you measure the altitude here for triangle ADC, the altitude remains the same, and that is why, because the altitude remains same and the base is also DC, the base is DC, that is why these two triangles will have the same area. So I can say, therefore, area of triangle ADC is equal to area of triangle DBC because of same base and altitude, right? So we have found out two pairs of triangles which have the same area within a trapezium. Now let's consider some more triangles. So now let's consider triangle AOB. Let's consider triangle AOB and triangle BOC, right? So let's consider triangle AOB and triangle BOC. Let me shade the BOC triangle with a different color. Okay. So these are the two triangles that are under discussion right now. Now these two triangles, they can be considered as having equal altitude. So consider that I draw a line parallel to AC as shown in the figure, right? So the altitude for both the triangles is the distance between these two parallel lines, right? And therefore what I can say is the altitude for the orange triangle and the yellow triangle as shown in the figure here is exactly the same. So what I will do is I will draw an altitude here. So I will draw an altitude here. Okay, and this altitude is for both the triangles. So therefore what I can say is these two triangles, they have the same altitude. I can definitely give a name for this triangle, but we want to understand it conceptually, so I won't draw the altitude. I will say that these two triangles have the same altitude, but they are on different bases, right? They are on different bases. What are the different bases? Triangle AOB has base of AO and triangle BOC has base of OC, right? Therefore, since these two triangles have the same altitude but different bases, the ratio of their areas, that is area of AOB divided by area of triangle BOC, the ratio of their areas will be equal to the ratio of their bases, which means area of triangle AOB divided by area of triangle BOC is going to be equal to AO by OC. If I were to just draw an altitude, let me draw the altitude now. You will notice that the altitude is same for both the triangles, right? So this is the height for both the triangles. You might be wondering how come the altitude for triangle AOB lies outside the triangle. That is, how come the altitude for the orange shaded triangle is outside the triangle. That is so because the angle AOB is an obtuse angle, and that is why the altitude lies outside the triangle, right? And therefore, we have used the property that if two triangles have the same altitude but different bases, the ratio of their areas will be the ratio of their bases. Let me just pause for a minute so that you can grasp all that was done here, and then we will continue. Okay, let us now consider some more triangle combinations. The next triangle that I want to consider is, let's consider triangle AOB and triangle AOC. Okay, I want to consider these two triangles. If you carefully notice, AOB, that's the orange colored triangle, and not AOC actually, ABC, yeah. So AOB is the orange colored triangle and ABC is the whole triangle. So AOB and ABC, they both have the same altitude again. They have the same altitude, but they have different base, right? They have different bases. So what are the bases? For triangle AOB, the base is AO, right? This is the base for triangle AOB. Whereas for triangle ABC, the base is complete AC, right? That is the entire base for triangle ABC. Whereas the altitude again can be drawn from the vertex B, and for both the triangles, the altitude remains the same, right? Again, for the orange colored triangle, you might be wondering how come the altitude is outside the triangle. The answer is because it is an obtuse angle triangle, obtuse angle at O. The altitude definitely lies outside the triangle, right? So Now I can say that area of triangle AOB divided by area of triangle ABC is given by, so AOB has a base of AO and ABC has base of AC, and that is why the ratio of their areas is AO by AC. Again, because these have the same altitude, these two triangles have same altitude but different bases. So you will notice that in this particular trapezium there are so many different combinations of triangles, and you can use all the theorems that we learned today to apply in these small triangles, right? So let us take some more combinations now, and let's figure out some more ratio of areas in the same trapezium. Okay, so let us now consider some more pair of triangles. The first pair that I want to consider in the diagram now is triangle AOD and AOB. So let us shade them. Triangle AOD is this triangle, the blue colored triangle, whereas triangle AOB is the yellow colored triangle. Now these two triangles, if you notice, they have the same altitude, right? I can drop an altitude from A on the side BD, right? So both these triangles have the same altitude, and again you might be wondering how come the altitude of AOB, that is the yellow triangle, is outside the triangle. That's because angle O is an obtuse angle, right? So that is why its altitude lies outside the triangle. And because these two triangles have the same altitude, I know that the ratio of their areas, so area of triangle AOD to area of triangle AOB, this is given by the ratio of their bases, right? So these two triangles have the same altitude, and therefore the ratio of their areas will be the ratio of their bases. So what is the ratio of their base? The ratio of the base is DO upon BO, correct? So ratio of the areas is the ratio of their bases. Now similarly, let's consider triangle AOB, that's the yellow triangle, and ADB, that is the whole triangle. Now if you think about it, consider triangle AOB, that's the yellow shaded triangle, and the triangle ABD, that's the complete blue triangle, right? So in these two triangles, you will now notice that they have the same altitude. Again, I can draw an altitude from the side, from the vertex A, right? From the vertex A to the length BD, and because they have the same altitude, the ratio of their areas will be the ratio of their bases. So I can say that these two triangles have the same altitude. They have the same altitude but different bases, and therefore area of triangle AOB divided by area of triangle ADB is given by AOB's base is OB and ADB's base is BD, right? So it is given by OB upon BD. Now I think I forgot taking one more pair. I can consider triangle AOD. I can consider triangle AOD and triangle ADB. So now I am considering the blue triangle, that's AOD, and the complete triangle ADB. So now let's see what property can be applied in these two triangles. These two triangles again have the same altitudes. They have the same altitudes, but they have different bases. And therefore, I can say that the ratio of their areas, that is area of AOD upon area of ADB, will be given by the ratio of their bases. So what is the base of AOD? Considering the altitude is drawn from the point A, the base has to be DO for triangle AOD, right? So the base is DO, and the base for triangle ADB, considering again that the altitude is dropped from the point A, the base has to be BD, right? Therefore, the ratio of their areas will be DO upon DB. So this is how I was able to apply the properties to these different triangles. Now this is the last triangle that I would like to consider. I have to consider area of AOD and area of BOC. So let us quickly shade the triangles that we want to discuss right now. I want to discuss area of triangle AOD, that's blue in color, and triangle BOC, which is yellow in color. I wish to discuss the area of these two triangles. So these two triangles, you will notice they don't have the same base, they don't have the same altitude. So now I am wondering of how to solve this particular question. What comes to my mind is, we know that the area of triangle ADC, right? So area of triangle ADC, let's write it down. We know that area of triangle ADC is equal to area of triangle BCD. Why is that so? Because the base is DC, same base DC, and equal altitude also. Right? And therefore, area of triangle ADC can be written as area of triangle AOD plus area of triangle DOC, that is equal to the area of the whole triangle ADC, and area of triangle BCD can be written as area of triangle BOC plus area of triangle DOC. Now you will notice that area of triangle DOC vanishes from both sides, and therefore what you get is area of triangle AOD is equal to area of triangle BOC. So area wise it means that these two triangles, area wise, they are equal. Of course they are not congruent, and they don't have the same base or same height, but still their areas are equal to each other. Okay, so these are the different properties that are related to a trapezium, which will be useful when we solve properties related to trapezium. The different concepts that we used were triangles with same base, same altitude, different base, different altitudes, and of course in the last one we just used the area propositions. So now if I were to pictorially represent, okay, consider that ADC's area and BDC's area is equal because same altitude and same base. Now I am subtracting the same area from both the triangles, which is area of DOC. So because I am subtracting the same area, the leftover areas are equal, right? This is what this particular theorem means. So let me again pause for a minute, and then we will conclude this particular segment. Okay, so we conclude that whenever you have different triangles and you are being asked for the areas and the ratio of their areas, or the connection between the ratio of the areas and the ratio of the sides, the different properties that we saw in this video are extremely useful, And I hope you understood what was done in this particular video.